Yes. Did I trace that? Okay. So you can see the accumulated result of like calculating the depending values, depending accumulator until the end. So you get a very explicit result at each step, and you could even think of it as like, if you stop the operation here, you have all the information to continue with the next step. So that's called like, this is an iterative process, and this is called a recursive process in for example, in the book, Now, one thing that's interesting is that there is a mechanical way to turn a recursive process into an iterative process. Give me any recursive process, oops, not just factorial, and I will turn it into an iterative process. And the key way of doing this is called continuation passing stack. So who has heard of that? Okay, so you've done it in the classes?
Oh, I've heard of it. I haven't done it.
Okay. Yeah, so it's kind of fun that you can do this automatically. And the point is that we are representing the rest of the computation as a function. So we're going to do factorial CPS. It takes a k for the continuation, and basically we have functions that never returns null. So here in this case we have k1, and in this case we want to do this call, and then kind of think we get a value back, and we want to do k over the result of applying this value to n, something like that. So let me just call this factorial CPS. And now, if I trace that, six, and then I have to provide an initial continuation, so I'm just going to provide the identity continuation. I get something like this, so it's kind of more opaque now. We don't know what is really going on in these procedures, but we also have no stack, use of stack, and that's a, in some sense it was, I mean, historically like continuation were the gateway drugs to program transformations, because basically once you put something in CPS, it has all these nice properties that allow you to do more transformation over this. So one property is that whenever you're calling a function, you're just jumping, unless it's a simple function, which you can do right there. So there's a notion of serious code versus non-serious code, but otherwise you're really never using the stack. Any questions on this?
So what are the advantages of not using the stack? Is it mostly like for static analysis, or?
Yeah, so in some sense, like if you can convert it quite nicely to not using the stack to some sort of anormal form, but there are even practical advantages, like if you're not using a stack, your garbage collector doesn't have to worry about a stack. So that's one thing. And there's also like other advantages to having this explicit representation of computation for resuming the computation at any point you want. So for example, but that's kind of a different perspective than just not using the stack. But it's kind of just makes things easier not to use the stack. But it is practical to use the stack for little things, but you can avoid having a stack overflow with like using the stack too much. It's also related to tail recursion. So if you're going from here to here, you can kind of handle this in your compiler as just one jump. And so you're completely avoiding any kind of accumulation of memory that can
I have a question slightly back just to the concept of the metacircular interpreter, in that it seems like because we're referring to the primitive operation sort of outside of the interpreter in some sense, it feels like we've abstracted away what the meaning of the primitives is. Is that correct? So it feels like we're just kind of, okay, everything's syntax now.
Yeah, so we've, well, we haven't, I mean, we've it's not so much that we've abstracted away that we've like like assume the floor has these definitions and we're using them and maintaining them, right? So there's this interesting paper, let me see if I can find it. This paper might be interesting to you because, I don't know if you know, but it's kind of like this idea that your compiler can hide information that is not obvious from the code. I need to put this a bit further back. But so this is kind of like, it stems from the same observation that basically the compiler is not spelling out everything. So we're not spelling out everything, but we are using the recursive definition. And another example that I want to show where we're not spelling out everything is, for example, in Prolog, we can also define a meta-circular interpreter. So it's very simple. It's just verifying kind of the search process of how you solve goals, but it's not making explicit what is the unification algorithm, what is like the way you, all the logic, sort of the logic variable aspect is kind of left implicit for the system to pick up. So in some sense, a meta-circular interpreter can feel like a partial definition because it's relying on an implementation. It's not like a definition like you would have a semantics or something. But yeah, it's interesting.
My question is about the CGS transform.
Yeah.
Is it possible to represent factorial CGS in a language that does not have proper tail clause?
So it's possible to represent it and get the benefit of having these explicit continuations you can resume, but it's not going to help you with your stack overflows. Okay, so we have that, and now we can play the same game with the compiler or the interpreter. But before we do this, let me just show you one thing you can do in Scheme is called call CC. So let's say I did +3 here. Something is wrong with it. So let's say we do call CC lambda k plus K2 plus K6, and then we put this in a loop like this. So this returns 6. Well, I guess my numbers are poorly chosen. I think we did 7. Yeah, so this returns 6 because what happens is that call CC is getting the remainder of the computation at this point. So you can think of it as lambda whole 2 times whole. That's the continuation at the point of the call CC. And then you basically have a handle on this continuation k, and you can call it. So when you're calling it here, you're jumping out with the result of whole being substituted for 3, and you get 6. So we can add a form like this to an interpreter that manages the continuation, but that's basically something you get for free if you have a continuation passing style interpreter. So that's what I want to show you, just to make a more mechanical transformation of this. But before we get there, why is this also close to more low-level programming in some sense? One thing we can do is define a while syntax. So I define this while syntax here. And then once I have something in CPS, I can do something that is called trampolining. So I can basically explicitly thump every invocation like this. And now what this thing does is that every time you call it, it kind of stops and returns a procedure. Like if it returns a procedure, you have to kind of invoke the procedure to get to the next step. But that returns another procedure. And if you invoke enough times, so you kind of resume the computation at each time. And you can kind of just have a driver loop for this. So for example, you can have a driver that takes a time, or takes something, and says while we have a procedure P, then we kind of just do P. Otherwise we return P, something like that. And now we can do driver factorial 6. Oops, did I do a mistake? There's an infinite loop. I'm not sure what I did wrong. Oh, I guess. Yeah, you're right. Thank you. That's it. So, I think this was right. I forgot the syntax of this thing, so something like that. Thank you. Okay, that works. So that we're just driving. And now we see that we've turned something that is, can be a pretty complicated arbitrary computation into something that is just like a simple while loop jump. So actually, to answer your question about whether this is still useful, if you do trampolining, you get the benefit of no stack overflows as well in this context. Yeah?
I will look at these by policy C because I would have thought that we would be multiplying 2 by 10, or that we would be like adding 7 somehow. So I think that makes sense.
I think you're right. I think it is confusing. I think the main confusion is that once you call K, it just jumps out of that loop. So you, and I guess in practice, it's kind of like people usually like to use the limited continuations because they're more composable, but with CoCC in practice, you can do useful things by using setback, saving the continuation, and reusing it later to jump out of things. Actually, maybe a useful example to show is, say, if you wanted to do like define products. So you have, like I guess maybe I'll leave it as an exercise, but one thing you can do is define products where, like, if you see a 0, you just jump out. So that's something you can do quite easily. Okay, so let's just see how we CPS interpreter. So it's a very mechanical thing. It might be a little tricky to do with such a big font, but let's see if I can manage it. So the point is that now we have an extra argument here. I'm just going to call it K. And every time I'm never just returning, I'm just using K instead. So we assume the environment is just, we haven't really CPS the environment or anything. We just assume we have a primitive function. So I'm just going to also use this thing like this and assume it's not a serious call because you can only kind of jump out when you have no strings. And now this is the first interesting case. So we're pushing this out. And then we're having lambda d k sub t. So we're basically saying, we're making explicit what is the remaining thing to do once you've done the evaluation. And the other cases are similar. So this one is also oh yeah, thanks. I'll just finish this case first. So here I'm missing this mistake. Yeah, so this might be a little more to do, but it's not super hard. But when you have two recursive call, there is a question that comes in: is you have to make a choice about order of evaluation. In this case, we left it implicit that whatever times, like whatever the regular order of evaluation is, that's what's going to happen. Here we have to make an explicit choice, and that's also part of the process of making it more reliable. So I would say V1 here. And I'm putting way too many times. So we have this, and then we have this one, and 2. And then we have to not forget the k, otherwise that would be a block where a computation or something like. So the other cases are similar. I guess the lambda case is interesting. The if case maybe is interesting because it's a special form. So that I think we just have a few left, so let's do them. So for if, we're again starting with this starting point. And we have lambda, let's see, and then we can do the if right there. And in here we can just pass in the k, because that's the result of the computation. And then what happens to the lambda? So that's kind of interesting. I mean, we have an evaluation in the body, we want to pass in some continuation there, but we also want to return the current continuation. So like intuitively what happens is that we're going to have to change our calling convention because we want our closures to now, like we want our calling convention, we want to have two arguments. We want to have the continuation that you know are the ones that will apply to lambda, and then we want to pass that here. And then we want to have k, because we are returning a lambda, so that's the calling it with k here. So we've changed our calling convention, and we have to also rectify this now. So here, when we're calling the argument, we just pass in the continuation. So before we ponder on this code, let's see if it even works. So MC environment stays the same. Testing details. And I'm going to define the ID continuation to the x. Okay, so that still worked. Well, this I haven't defined, so that's okay. Okay, so I think I missed one of those cases. So let's just take a quick look at the cases that I might have missed. So yeah, so here I made a mistake. I should have also fixed the order of evaluation. So that's the result of the F. And then do yeah, so I made a mistake here because I went a bit quickly. So here what I want to do is have the lambda F, then I want to do the lambda V for the value, and then I want to do my calling convention, which is F V K. So that makes more sense. So let's see if that works. Oh, and here this should go inside. Okay, and here I have extra things. Okay, this worked, and now we can try the fancier example. And it worked too. So now we're just a small step from writing call CC in this interpreter as well. And we can just add a case for it. It's really just a form like others. So we can add it here. Yeah.
Is it good at all to think of call CC as like throwing an exception?
Yeah, so there is a connection. So in some sense, the jumping out is similar to throwing an exception. So you can model call CC like, you can model exceptions with call CC like routines.
Can you jump out and never jump back in? Or is that kind of?
So if you pass around the continuation, you can use it again to jump back in. And that's kind of what you can do with literally anything. So it's a whole programming style to play with like this first order continuation. Like sometimes there's even this thing where you want to have a failure continuation and a success continuation, and kind of not just have one continuation, but like what do you do when you succeed, what do you do when you fail, and that's a common form for logic programming.
I'm sorry, to go right off of that. So if you have these failure and success continuations, it's basically saying later on you can pass around the code to evaluate later on.
Yeah,
if you
so
pass it.
I mean, maybe I have some code. I think I might have some code in the kernel from the class that shows this kind of thing. Okay, so I guess this is an example where you're doing a web first search and you're doing it by having a success and a failure. And so you're jumping around like this. Does this concretize what you have in mind? You have something more complicated in mind, I guess. But you can do a lot of non-deterministic backtracking and things like this using this kind of approach. Yeah, so here, for example, the failure just raises a not found, but in the process of searching, you might actually say, okay, here's an item that path you can take instead of failing. So you're composing these things kind of nicely. Okay, so call CC. So first, the argument to call CC is anything that evaluates to a procedure. So we have call CC, now the procedure of one argument, right? So we have to evaluate that. So we can just do evaluate gather of x, and then we get the function. And now what we want to do is actually call that function, but we want to pass in the continuation. So there is a small catch, which is a little subtle. We have this high order representation for stuff. Our continuations have been represented by just this one argument thing. So we have to kind of convert. So what we want to do is do f. We want to do, k. And we want to pass it some function that takes a k and packages the f like that. Something like that. So do you see why this extra argument came to play? Because basically we have to pass in some function that the system understands. Our system only understands closures. Closures take two arguments, so we have to convert a continuation into a closure. passing. So I did so I need to, this is actually K. And then I need to do, I don't know if I'm overdoing this, but I think basically because I'm doing it like this, I can just do it. So let's just try it before we decided to even try to explain it, because I'm not convinced that I did the right thing. So if I do call CC, inbound variable key. Perfect. Okay, so that worked. So maybe we can just take another look at it now and try to understand what I did. So first, we are calling F because that's the convention. That's the, let me actually put this here as well. Oops. Okay, so let's just so here we have 6 because what happens is that when we see the call CC, we are getting the continuation here, and we are passing it to this lambda function as k. So we are calling the lambda function. So that's precisely what this part is doing. It's calling the function that we just evaluated with this continuation package as a function. And then it's also using the continuation here in case we.
So what's the K0 that makes it, because instead of a normal K0, we're like using different continuations?
Yeah, that's a good question. I think it's because we are not, we are really wanting this thing to behave like a continuation, so we're just jumping. So there's no anchor for the case here. It's just an artifact of a calling convention that we're going to be passing that thing. But yeah, I agree it's quite subtle. And sometimes, actually, this might look easier in first order as well. So let's just maybe take a look at this. Well, I guess I didn't actually define it here. But yeah, I mean, in the first order, you might have like a special tag for continuation with a different calling convention. So that might just simplify things. Okay, so one thing we showed is that we can have these meta-circular towers, and then there is this other model of affection, also, I mean, from the early 80s, and there was quite a bit of work in the 80s about that. So the idea is that basically we were kind of associating verification with going up a level and affection with going down. Okay?
Is quoting gratification
So quoting is kind of like verification. Right? So you take a program, you quote it, you get data that represents that program. So the way I like to think of it is so like verify takes program and return data, and reflect takes data and installs it as a program. Now in practice, I mean, these things doesn't necessarily mean you're going up a meta level, but you need some way when you have, when you've coded back and to give it meaning, right? So often we can associate verification with going up a level and reflecting with going down. And then you can have a sort of reflective towers of interpreter that is really just like allowing you to go up to the meta level and the meta level of the meta level, and every time inspecting the programs at that level as data at the level of things like that. And so there is a few different, the history is there's like this tree which coined this idea of towers of interpreters. And then there's brown, long, that basically explore this idea mostly in scheme or derivative schemes, and then there's also pink and purple that explore confirmation.
Those are nice names, or?
Yeah, these are names of reflective towers of languages.
Oh.
Yeah, so they're all like it started as hair color, but I didn't get the memo, so I did pink and purple. So maybe we can talk a little bit about brown, black, brown, and purple. Let's look at like the brown model, which is kind of in the paper. They have a very nice limitation for what that means. And really, at some core level, it's a question of keeping track of these streams of environment continuation pairs. And they call this meta continuation. So you have these streams of continuation, and you can shift up and go up and do things at different levels. So what's interesting is it's not a big stretch to go from something that is CPS to this thing. And the CPS comes in because you naturally get verification of resuming computations. Like you get continuations for free in the tower as well, but you need to have the CPS machinery for that. So this is first an evaluator in CPS that I have. So I guess it's kind of like an extension of what we saw, except okay, closure are tagged values and things like that. So it's a little bit yeah, it's just different representation between higher order and first order. And then the tower version is really just basically doing this meta constant. So it's really just making explicit that you can get meta continuations, and meta continuations are these streams. So how are we representing streams? We're representing them as something where you have an element of the stream, and then the tail is just a thumb to basically do it. But if you had like you can also use like lazy evaluation to create the streams or anything like that.